A great welcome to the series on Abaqus. This is part C of tutorial number 12, which explains the use of Abaqus in the analysis of a bolted structural bracket. Now, regarding the problem statement, the detail is already provided in part A of the tutorial, and therefore it will not be repeated here. So the part C of this tutorial covers essentially the modules, mesh, job, and interpretation of results through the visualization module. So let me take you to the Abaqus. Okay, fine. So we will start this part C of this tutorial with the mesh module. Now, in order to streamline the meshes properly, I would like to consider some concentric circle around this bolt holes. So, and this will be done through the sketching. So we'll go here and do the sketching. And okay, we have to first of all select the faces. So let us select the faces. Okay, we have selected the faces, done. Now let us select an edge also. We will select this as my edge. Okay, so now let us start drawing the circles around each of these bolt holes, and we'll make this a circle a little bit larger. Let me say that a diameter of 50 mm. So let us start having these circles around each of these bolt holes. Okay, so let us dimension it as 25 mm radius. So this will be my 25 mm radius because of 50 die. Now, as usual, let us do the linear copying. So this is my end it is to be copied, done. And in one direction we have only two members, and this will be spaced at 130, 130. And in the other direction we have got three, and that will be spaced at 150, 150. Okay, so we find that yes, we require the flipping. Okay, fine, so done. So this means that now you can see that yes, around each hole, around each bolt hole, we have drawn a concentric circle that is of radius 25 mm or a diameter 50 mm, because this will help us to do the proper meshing activity. So now, having done this, we can still proceed for the meshing. So let us go directly to the mesh. Okay, fine. So let us first of all set a global parameter for the column element. We'll set a global size of 30 is to a little bit larger. We'll keep it as a 20 mm. That's okay. And now we will assign some local seeds, especially for this area, because it consists of a smaller circular arc where we also expect some kind of stress concentration. So, so we shall use a little bit smaller local seed. So go for the local. So first of all, let us select the regions where we require the. So okay, I will just select this as by the triangle. Okay, so let us start selecting individually all this. So we want to assign the local seeds to these curved areas. Okay, that's okay for us. Done. Now I would like to use a smaller size. Let me say that this is something I would like to keep, say, less than the global size. I would like to keep it, say, 10 mm. That is almost half the global size. So that is okay. Fine. So we did the local seeds as well as the global seeds. Now we can proceed for the meshing technique, selecting the meshing technique. So we'll go here. So we'll select the regions. This is my inter region. Done. And here I would prefer to go for the sweep because I have got the halts and the algorithm will be middle axis. Okay, fine. So now let us go for the meshing activity. So but before the meshing activity, let us also do one thing. Let us select the element as well. Okay, so select the region. Done. Okay, fine. So we'll use this is a standard 3D stress element, linear, that's good enough. And so note down the element type C3D8R. That's an 8-noded linear brick element with reduced integration. That's okay for us. So let us proceed now for the meshing. Yes. Okay, so let us see the how the meshing is done. Yes, you can see that the meshing is done properly, and there is no kind of you know irregular meshing at all. So now you can see here the advantage of okay, providing an additional hole over here because it has reduced what we call as the transition, and therefore we are having almost a very good meshing here. Now what I would do is here I would like to see in the 3D also. Now here in the 3D you will find that yes, along the circular hull, okay, we have got a little bit deeper element here this dimension. So I would like to divide the thickness of the top flange also into two through the local seed technique. So let me may have it this way. Okay, so I'll just zoom this. I want to divide this top flange only because the top flange is the location where my holes are located into two through the local seeds. So do it also through the local seed only. Select this edge. Okay, that's okay for me. Now let me go to the other side. It's okay, fine. So now let me also select the other edge also. Yes, fine, that's good enough. So done. And here I want to use by numbers. I want to split this the flange plate, the top flange plate in two segments along its thickness. Okay. So delete the old meshes. Okay. Now let us again regenerate the mesh. Okay. Yes. So you can see that yes, the top flange is now divided into two. You can see the mesh once again. And now if you see that along the thickness, you can see that now we are having a far better way of the meshing because we have divided this thickness into two. Now similar to the column flange, let us start meshing the flange portion of the bracket. So just like the earlier part, we have added here additional circles around each bolt hole in order to streamline the meshing. So let us proceed for the definition of the global seeds. Here we have set a global seed of 15 mm and the local seeds that we have already set around this curved portions. So we have that is already selected and that is set to be 8 mm. So now let us proceed for the proper mesh control procedure. So select the center region, okay, done, and we'll go for sweep middle axis. So it is X element shapes. That's okay. So now let us proceed for the meshing. So you can see that yes. So you can see that yes, it is meshed properly around each hole. There is no problem, and we have also done the meshing around the thickness. If you see the isometric, you can see that along the thickness also we have provided a local seed of two numbers. So this means that the meshing activity for the flange portion of the bracket is over. Now let's quickly do two things. One is the element type. We can select the entire one. Okay, so it will be the same element as the column. It is you can see that here is C3D8R, so that's okay. Now let us also quickly verify the mesh here. So verify the mesh. So select this entire mesh, done, and we have asked Abaqus to highlight all elements with an aspect ratio greater than 5 and with angles less than 10 and greater than 160. So just highlight. So here we find a very good statics, that is the aspect ratio greater than 5 it is 0%, average aspect ratio is 2.48 is very good, and maximum it is 4.965 and there are no warnings. So it means that this is acceptable for us. So now let us proceed for the other component, that is the bracket web. So this is the bracket web here, and here what we shall do is that we will assign, we don't have any kind of an opening, so it is good enough that we assign a global mesh size 15 should be good enough for us, and no local seeds will be required for here. And let us proceed for the mesh control procedure. So we will go for the hex dominate here and sweep and advancing front. Okay, that's okay for us, and we shall proceed for the meshing. So yes, so you can see that yes, so here you have got a combination of okay, so you can see that some triangular meshes are also there, but this is good enough for us because here we don't find also any requirement to divide the thickness into two parts. So let us quickly go for the mesh verification. So select it, so done, and this okay highlight, and here we find that everything is good enough for us. The average, the worst aspect ratio is 2.32, and there are no warnings. That is good enough. And the element type, obviously it will be the same C3D ATAR. Done. So you can see that is selected C3D ATAR. That's okay for us. So now what is remaining is only one element, that is the bolt. Okay, so here if you remember, we have a partitioned, okay, we have partitioned the bolt in such a way that uh, we will end up with a good meshing arrangement. So we have divided this bolt into four segments along the longitudinal axis. Also using the datum plane, we have cut into three pieces. So let us go for a global size. So this is let us keep it as a 3 that's okay for us, and here no local seating is required. Now regarding the mesh control procedure, select it. Let us use the same sweep medial axis with the hex elements. Okay, so that's okay for us. So let us go for now the meshing. So yes, so here you find that yes, the meshing is done properly. There is no problem at all, and you can see that this is all because of the a lot of partitioning we did, and we have divided this entire complex shape into small segments. That has finally resulted in a very healthy mesh as shown here. So let us similarly go for the uh, mesh verification. So done here, so we'll use the same one highlight. Okay, so we find that here again the mesh configuration is very good. Worst aspect ratio is only 3.19, and we don't have any elements with a more than 5 aspect ratio, and there are no warnings as well. So this means that we have completed the meshing of all the components. We can now straight away jump to the job and submit it. So now let us proceed for the job module. Here we shall create a job. So create. So let us call it as a job bracket. Job bracket D. Okay. So continue. So it's okay for us. And now submit the job. So you can see the status here. You can see that here yes, status it is submitted. Now once it starts running, you can start monitoring the results also. Okay, fine. So the analysis is run. Let us start reviewing the results to the visualization module. So let us first start inspecting the von Mises stresses for the different components of this model. In particular, the bracket, the column flange, and the bolts. So let us first see the von Mises stresses. So let us first remove the bolts from this model so that it looks a little bit more comfortable to analyze, because we'll do the bolt interpretation results later. So just remove it. Okay, fine. So now if you look into this variation, you will find that yes, as far as the bracket is concerned, we find that there is a maximum stress around this portion, which is something around say 235. Is well below the yield stress of 355. And again, if you look into the flange plate also, we don't have much issues. The stresses are around say 250 Newton per mm square. We don't have problem. So now let us see the condition of stresses in the column flange. Obviously, the column flange will be critical in this case. So what we do is that let us just remove the bracket portion from this viewport. So we'll select the both these bracket components and remove it. Okay, fine. So we find that yes, as expected, we have the stress, much a large stress concentration in and around the hall. Look here, in and around the hall, we have got a larger stress concentration. And as expected also, we know that the bolts in the top row will be under tension and the top bolt holes, okay, the portions of the column near the top bolt holes will be very critical. And if you see the bottom holes, find that there are no much stresses and all. And as far as the criticality is concerned, the top portion is more important for us. Now let us find out, are there any column elements that has surpassed the yield stress criteria? So we can go here, set this, specifies the limit. Okay, let us have it as a, set it as a, say, for example, say 355. That is our apply. Okay, yes, we find that yes, a portion of the bolt hole, okay, that is already yielded. We, as indicated, the stress levels are higher than 355 Newton per mm square. So that is all regarding the stresses in the column flange, which is very critical to us. Now let's quickly see some of the deformations. So if you see the U, that's the deformations, because that is also important for us. Let us add other portions also. We will add, for example, all the bowls, add, and we can also add this bracket, add. Okay, fine. So now let us see the, we will change these limits. We'll keep it as auto compute, apply. Okay. Now let us see the deformation in the set direction. Obviously, when the bracket is loaded, we expect that yes, there will be some out of plane bending of this. Okay, out of plane bending of this bracket component, also the column flange. So let us see the U3. So this is U3. Okay, U3. Now you can see that yes. Let's just see the zoom this portion. So you'll find that yes. Let us this portion. It's a little bit moving. So let's see the elevation. That will be better for us. Sorry. Yes. So let us zoom this portion and let us increase this scale ratio a little bit larger for the deflection. Let me say that this is a 20 mm. Apply. Okay. So now here you can find that yes, on the top there is a loss of contact. So how the entire structure has deflected? Let us see it. Yes, you can see that yes, it is gradually increasing. Yes. So here you find that there is a loss of contact. Okay. Okay, fine. That is good. And now one more very important thing we want to inspect is here when we have increased the scale ratio, we have seen that yes, a portion of the column, okay, it has a buckled. There's a column that is buckled under this load. Okay, now let us see, for example, this has happened in the outer plane deformation, that's the X. So let us do one thing. Let us keep this deformation scale a little bit smaller, that's a 10, apply, okay. Now we would like to see the U1 variation. So this is my U1, okay, yes. So in the U1 you will find that yes, we have got a 10 mm, right, 10 mm. And the critical portion, as you can see that it is your column web. Okay, yes, find that yes. Obviously, because when the bracket bends, we expect the tension on the top and the compression at the top. Where this compression force is transferred from the bracket to the column web, this column web is not good enough for carrying out this taking out this compression loading. Accordingly, you can see that yes, we have, this web is subject to some kind of a buckling. Maybe that we may have to add some kind of a stiffness, or we may have to add some kind of a cover plate, etc., in order to stiffen this column web. Now, having seen this, let us go and investigate the forces in the boards. That is also very important for us. Obviously, as far as this kind of arrangement is concerned, we expect that the bolt tension will be maximum in the top rows and it should be practically zero at the bottom one. So let us just start investigating the bolt forces. So we shall go over here, and out of this what we can do is we can just remove all these elements which are not required. So this is removed. We want only the bolts, and okay, that's okay for us. So now let us just do this one. Okay, fine. Now here, okay. So let me select the top, for example, one bolt from the top row and one bolt from the bottom row. So let me see which way. So I know that yes, this will be the bolt one. That's the topmost row. So I will just remove this balance bolts also from this. Yes. So this is a bolt in the topmost row. Let's find out what will be the tension in this bolt. Okay. So in order to find out the tension, we can make use of this activated deactivated view cut manager. And obviously, if we are interested in the tension, we have to see the variation of these forces in the set plane. So select this as set plane. Okay. So you can say that yes, it has started showing the results. So let us start moving the plane along the z axis, right? And look into this is your tension force, and that is 1.092 into 10 to 5. That means it's all as good as 110 kilonewton. Okay, so we find that, the maximum tension it is around say 110 kilonewton. Okay, so as we reach the shank portion, obviously should reduce because the area is increased. So we find that the shank is subjected to a constant force of around say 110 kilonewton, and also ensure that you can also obtain what is the force in the bolt at any time frame. You can see that, for example, if you start from the zero frame, you will find that yes, it is increasing to say 71, 83, 94, 110, etc. like that. So this way you can also see the variation of the bolt force for the various time frames. So this is all regarding the top bolt. Now let us also select, so note down the maximum force in the top bolt, that's a around say 110 kilonewton. Now we can also select one bottommost bolt. For that, what we can do is we can include one. So this should be the bolt. Probably I think that in the bottommost row. Yes, we can add that also in all this thing. So let me also select this one bolt. Add. Just remove this. This is not required for me. So I require only one bolt, which is in the bottommost portion. So add this. So yes. So this is the bolt. So let us find out what will be the variation of the tensile forces. So obviously we expect a lesser tensile forces here. So let us start seeing the tension forces around this. Yes. So look here. The bolt forces in the bottommost row, it's of the order of say 8.8 kilonewton or maximum say 10 kilonewton if you see. Yes, it's only 8.8 kilonewton. Okay. So this is as expected as well. So this indicates all this result evaluation and the conclusions indicate that yes, Abaqus has properly modeled all the contact between the various elements, and the behavior of the various components are in line with our expectations. And it is important we check each and every component, and to ensure that it is the engineer's responsibility to ensure that each and every component has a behavior that is in line with our expectations. If there is a deviation, we need to investigate it. Okay, so that's all for this tutorial. We will come with exciting tutorials in the coming weeks. Till then, bye.